Even though I have made the claim that ordinary least squares is going to be a biased method of estimating capacity, I'd like us to spend one section going through how you would go about deriving ordinary least squares, because the method is going to be similar to how we end up deriving the total least squares solution. And then we can compare the two different methods in terms of the results that they give and the complexity required in the computations and so forth. Both the ordinary least squares method and the total least squares method, when we apply them to a battery cell capacity estimation problem, are looking to find a constant Q hat, which is an estimate of capacity. Whenever I use hat, it means estimate. So that y equals or is about equal to Q hat x is satisfied. And remember that y was the integrated current and x is the difference in two states of charge. We are going to be using vectors of data. Now, ultimately, we hope to come up with a recursive method so we don't have to store these vectors, but at least in principle, mathematically, we're thinking about using vectors of measured data, x and y. And here, at least for the time being, for the rest of the chapter, I'm going to use a boldface x and a boldface y to indicate that I have vector quantities as opposed to scalar quantities only. Looking at one component of x, we'll call it x sub I, it's the ith component, and the corresponding y sub I component in y, the xi, yi forms a data set from data collected from a cell over the same interval of time. So over the ith interval of time, xi is the change in state of charge, so the state of charge at the end of that period minus the state of charge at the beginning of that period. That delta could be negative or positive. And y sub I is the accumulated ampere hours that pass through the cell during that same period of time. And those two, if there's no noise, should fit a relationship that y is equal to q hat times x. And we have this reminder here that in continuous time, we would use these equations for xi and yi, and in discrete time, we would simply have the summation-based formula instead of the integral-based formula. I need at least one data point to be collected to be able to do this estimate. I think that sounds reasonable. I need x equals qy. I need to have at least one x to fit and one y to fit, but usually we would have many data points to try to minimize the impact of noises on our estimate of q hat. The ordinary least squares approach, as we talked about in the previous section, assumes that there's no error on the x coordinates, which are the state of charge estimates, but that there can be errors, zero mean errors, on the y coordinates, and we model the data then as y equals qx plus delta y. And notice that we are using vectors here, so the vector of all y measurements equals the scalar q times the vector of all x measurements, and the differences then are the delta y vector, and delta y is some measurement error. And in this figure here, I've tried to indicate that. So this line is y equals q hat times x, and I'm trying to fit a line to the measured data points. The measured data points are these circles, and so I've got 1, 2, 3, 4 data points in this example, and they look a little bit, if you've seen Star Wars, like the TIE fighters, because what I've drawn are the error bounds. So perhaps I actually know what the variance of the error is in the y coordinate, the accumulated current, Maybe I don't know. But if I do know that, we're going to see that that is going to be taken into account in our estimate, because a point that has small error bounds says, oh, there's very little noise on that. I've got a fair amount of confidence that the measurement is an accurate measurement of the truth, whereas a point that has large error bounds, we would say, ooh, I've got less confidence that that is accurate. And so we should probably, if we're trying to put a straight line through these data points, we should probably treat, if this is one standard deviation away, the one standard deviation away from the measurement the same, even if one standard deviation is really big for one measurement and really small for another one. So you can see that these two data points, while they are farther away, the left one is farther away from the line than is the right one, they're both about one standard deviation away from the line, so in a normalized sense, they're about equally distant from the line, and that's what we're going to look at. We are assuming that the delta y vector is zero mean, that the noises are Gaussian, and the variances are known. So the standard deviation is sigma y sub I for the ith data point, and it's sigma squared y sub I is the variance. And the variances do not need to be equal to each other. The ordinary least squares will try to find a slope of true cell total capacity, an estimate of that minimizes the sum of squared errors on the delta yi's. And we're going to do it in a weighted sense, so that we weight the error, like we said, by the uncertainty of the measurement. Whenever we're doing some kind of optimization, and here we are, we're optimizing a Q hat so that we minimize, in some sense, the distance between the line and the data points, the weighted distance in our case. Whenever we do an optimization, we need to find a function that describes the cost of making an error in our optimization. And so we call it a cost function, or a merit function sometimes, if you want to think about it in the opposite way. We're either maximizing the good, so maximizing a merit function, or we're minimizing a cost. Here we're minimizing a cost, but we still call it a merit function. So chi-squared WLS. The subscript is the weighted least squares. And chi-squared is interesting. This actually is a chi-squared random variable because we've made assumptions about the noise being Gaussian and so forth. And the sum of squares of Gaussians is a chi-squared random variable. We don't really take that into consideration in this section, but it's just interesting to note that that is true. The function we are going to minimize is this. Little y sub I is the measured data point, if you will. So little y sub I is the actual integrated current. Capital Y sub I is the point that little yi maps to on the line. If I go back up to here, this might be little y sub 1 is the actual measurement, but capital Y sub 1 is where that measurement maps to on the line. And this would be capital Y sub 2, capital Y sub 3, capital Y sub 4, Y1, Y2, etc. for those data points, assuming they're organized in that order. So we're minimizing, the cost is the distance squared between the measurement and the line that we are fitting based on the measurements. And so we're taking that distance, we're squaring it. That's pretty common to do in optimization. We would usually like positive errors and negative errors to be treated the same way, and squaring accomplishes that. And squaring also treats big errors with more emphasis and small errors with less emphasis, which is appealing. And it also ends up with a solution that's mathematically computable, and that's probably the biggest reason why we do this. So it makes sense and it's computable, so all that is good. We take the error squared and we divide by the variance of that measurement. As we said before, we're really thinking about scaling the distance based on the quality of the measurement. So a high variance means the measurement doesn't have very good quality, so we don't weight that cost as highly. But a small variance means we have a lot of confidence in that measurement, and we do weight that very highly in our cost function. So overall, we are summing up the squared normalized distances between the measurement and the line that we are fitting. The assumption is that the line we are fitting, the point, is capital YI is going to be Q hat times lowercase xi. So we just take the x associated with the data point and we keep that. We don't change the x in any way because the x we assume is noise free. And then the capital YI is simply Q hat times xi. We want to optimize by finding Q hat. We want to find the best Q hat to minimize this cost function, this merit function. One way of doing it is to take the derivative of the cost function with respect to the variable Q hat, and then set the derivative equal to 0 and solve for Q hat. That's what we're going to do. And we have to be a little bit careful when we do it, but we'll take the derivative of this expression with respect to Q hat. Partial of cost function with respect to Q hat. Notice Q hat is in the numerator, and taking the derivative of that, it's in the numerator with a squared. So I'm going to have 2 times the derivative of the inside, and the derivative of the inside with respect to Q hat is minus xi, so it's minus 2xi times yi minus Q hat xi is what we get. The thing that we need to be very careful about is that anything with a subscript I must stay inside the summation. It cannot come outside the summation because the variable will change from summation index to summation index. When I is 1, I might have a different value from when I equals 2 or 3 or 4, so I have to keep everything inside. The minus 2, of course, is not a function of I, so I pulled that outside. So we have minus 2 times summation equals 0. We rethink of the summation as 2 summations. So I've got minus 2 summation I equals 1 to n of xi yi over sigma yi squared. And then minus minus plus 2 summation I equals 1 to n of, it's going to be Q hat xi squared over sigma yi squared equals 0. So simply expanding this and writing it as 2 summations instead of 1, notice that Q multiplies everything in here, and Q is not a function of I, so it can come outside. And we can divide both sides of the equation by 2, and we can pull this over to that side of the equation, which gets rid of the minus sign, and all of that gives me this here. Q hat times the summation of the x squareds divided by sigma y squareds equals the summation of the product of xy divided by the sigma y squareds. We cannot multiply both sides by sigma y to make it go away because it's a function of I. It's not going to be the same for every summation index. I have to leave it inside. But I can write this as one big lump and write my solution for q hat to be this big lump, the sum of xy divided by sigma squared, divided by this big lump, the sum of x squared divided by sigma y squared. So far, we have what we call a batch solution. This solution is one that if I have the entire x data set and the entire y data set and the sigma data set, I can do these two summations and divide them, and I've got an estimate. I would prefer to have a recursive solution, which instead of having to keep the entire data set, simply keeps a couple of recursive variables, and I can add a new data point without increasing my memory storage. You can imagine in a battery system we might be updating the capacity millions of times possibly over the life of the vehicle, so I don't want to have millions of storage locations to store the xi and the yi. I'd really like to have only a few storage locations that allow me to compute the estimate and update the estimate whenever a new data point comes along. With that in mind, we define a variable c1, n, where n is my time index of my latest measurement. So notice that instead of going all the way to capital N, which is the end, I have c1 n goes up to some arbitrary index. And it looks like this. And we have c2, n, which looks like that. So if I had a computation of c1n and c2n, then we could say q hat n is the c2n divided by c1n. And q hat n is my estimate of capacity using data up to and including the time index n. What's nice about the c1n and the c2n, the way they are written, they can be updated recursively. So I can write c1n equals sum I equals 1 to n of xi squared over sigma yi squared, and that's equal to the sum I equals 1 to n minus 1 of xi squared over sigma yi squared, plus the nth term, which is xn squared over sigma yn squared. So this is an equation that can be updated. If I have this here is c1, n minus 1. c1, n is the previous value for that variable plus a very simple update to it. And we have that written down here for c1. We can do something very similar for c2 and say that c2n equals c2n minus 1 plus xy over sigma squared. Now I've got constant storage requirements. I need to store two numbers, and only two numbers. Every time I get one new data point, I update c1, I update c2, and then I update my q hat. My q hat is equal to c2n over c1n. But I only need to store two things, and I can throw away the xn and the yn because I never need them again. Whenever we have something recursive like this, though, we have to find a way to initialize the recursion. This turns out not to be hard to do. I guess if we didn't think about it very long, we might simply set the two variables to 0. And so whenever I get a first measurement, I'm basically initializing c1, 1 to x1 squared over sigma 1 squared, and c21 is x1, y1 over the sigma y1 squared. We could do that. I think that ends up though with a bias in, well, not a bias, yeah, a bias in your initial estimate that over time might be corrected. I think it would be better to initialize a little bit more cleverly than that. Presumably, we know that the nominal capacity of this cell. We can go over to it and read it off this side usually, and say, oh, this is a 2.5 amp hour cell, so I know Q nom. It's not a perfect estimate of the capacity of this cell, but it's better than 0. And we know that we have that capacity over a state of charge range of 1. So we can use this when we are computing our estimates. So this, if I'm charging my cell basically for 100% state of charge, a range of 1, my capacity would change by Q nom amp hours. We make this synthetic 0th measurement. It's not a real measurement, it's just our observation from the manufacturer, where x0 equals 1 and y0 is equal to the nominal capacity of this cell. And we still need a value for what sigma is, and if we have any idea what the manufacturing variance of that capacity might be, so from cell to cell, how different is every cell away from Q nom at the beginning of life, we would set that variance to be the sigma squared y0. And then we could say that C10 is 1 over, so this 1 over sigma y0 squared, and C20 is Q nom over, so this over that manufacturing variance. One other thing that we can do is recognize that the capacity of a cell is going to slowly change over time, and the equations we've looked at don't really acknowledge that fact. They say that Q is a constant and that measurements at time 0 of capacity should be treated in exactly the same way as the most recent measurements, when in fact the capacity was different at time 0 from now. So if I collected lots of data, my initial data might look like this because it has a high slope because of high capacity, but later on the data might start looking like this because my capacity has gone down and the slope has gone down also. So if I try to mix all of these data points together to estimate what is the true capacity of the cell right now, it's going to have to make a compromise and try to put a line in between. It's not ever going to catch up to where we are right now. So this would be better than this. Of course, I've exaggerated. We know capacity changes very slowly over time. So it wouldn't be this bad, but the fact still remains that it would be nice to adjust this methodology to put more emphasis on recent measurements, x and y, than we do on the very distant past measurements of x and y. This is a fading memory we want to have. Instead of remembering perfectly all of the past data points, we want to pretend, in a sense, that we have we forget progressively what the past measurements were so that we can put more emphasis on the present ones. The way we would do that, we have to go all the way back to the cost function and modify the cost function to put more emphasis on the most recent measurements and less emphasis on the most distant measurements. We do that and we make something called a fading memory weighted least squares cost function by introducing this term here. Now there's nothing that says that this is the best way to have fading memory. It's basically a geometric that puts weight on the data points like this. If this is time and this is data, it's weighting the most recent heavily, and we have this geometric progression. As we go into the past, there's less and less emphasis placed on those data points. It's not magic. It's chosen simply because it makes the math work out really well. And so there might be other things that you could think of that would be a better idea conceptually, but the math might not work out quite as nicely as this does. So if you look at this, if I is equal to n, then my weighting factor is gamma to the 0. No matter what gamma is, that's just 1. So I put a weight of 1 on the nth data point, the most recent one. If I equals n minus 1, then I've got gamma to the power 1. And we think of gamma being between 0 and 1, but probably really, really close to 1, like 0.9999 or something like that. So we don't want this to decay too quickly, but we do want some decay in our weighting of past data. So if gamma is 0.9999, then the previous data point is weighted like that. The one before it with 0.999 squared, the one before it with 0.999 cubed, etc. You can see that we get this kind of a shape and how much we weight each squared error, normalized squared error in our cost function. Now, I'm not going to go through the steps of the derivation because they're really boringly similar to what we did. You can go through them yourself pretty easily to convince yourself that this is correct. The solution becomes this. Q hat is this summation of weighted terms divided by this summation of weighted terms. You can see where the gamma comes in. And this is where it's nice. We can again compute two different quantities in a kind of a recursive way to keep track of things. So the denominator term is still a C1 term, but notice I'm using a tilde notation whenever there's a gamma. Whenever there's fading memory, I use tilde, and whenever there's not fading memory, I don't use a tilde. And then C2 tilde is the numerator term, like this. So again, Q hat is C2 tilde divided by C1 tilde. Why did I use this funny weighting? Because it breaks down beautifully into this recursion here. C1 tilde is gamma times C1 previous plus the new data point, and C2 is gamma times the previous C2 plus the new data point. The weighting was chosen in such a way that when you get to the final answer, it is really simple to do. I don't need any more memory than I did for the unweighted version. I need to store two variables. I update each variable by first multiplying by gamma and then by adding this new data point into the solution. So you can see that we're really doing a kind of a low-pass filter with this gamma operation, and the gamma is the pole location and the z-plane. So if I choose z equals 1, I've got a pure integrator which remembers everything from the past, but if gamma is a little bit less than 1, I've got a low-pass filter that is slowly forgetting the past and is putting more emphasis on the present. Summarizing this section before we go on to look at a total least squares solution that's derived in a similar way, we see that these solutions have a number of properties that are quite nice that we would hope to have in our capacity estimator. First, they give a computable solution for Q hat. That's what I really mean by closed form here. It's an algorithm that I can update without optimization in real time. I've optimized the math to give me equations that I can update very simply in real time. I need to be able to multiply things, I need to be able to divide things, and add things. That's it. Simple math is required, no trig or anything like that. The solutions we see can be easily computed in a recursive manner, and we can add this fading memory with a very, very simple change to the original setup so that we can adapt Q to adjust for true cell total capacity changes over time. Those are really nice. It's biased, but it's nice. We'd like to come up with an unbiased solution that has these properties, if at all possible. So let's go look at the weighted total least squares solution next.